Hello students, welcome again to another lesson for maths. Now today we'll be continuing with our revision session. Okay, and the topic we're going to be looking at is not a completely new topic to you. It's a topic we've actually covered in class before, rational and non-rational numbers. But some of you have actually been asking me questions relating to some of the questions we did on this topic, which suggests to me that you haven't completely understood the topic. No problem. So that's why I'm bringing this back and then going over very quickly. And then of course, if time permits, towards the end, we'll go over the last three questions I gave you to try out as homework last week on trigonometry. Okay, so we'll go over the corrections to that as well, because some of you are asking me to go over the answers. Okay, so once we've gone over the lesson on rational and non-rational numbers, we'll look at the questions I gave you last week as homework on trigonometry. Alright, so if you're ready, let's begin. Now, of course, again, the questions I'm going to be giving you here, I will upload on the school portal along with the schedule for the lesson. Okay, so I'll suggest you download that and then have it with you, just in case you cannot see the questions here properly. You will see it a lot clearer in the download copy. Alright, so let's proceed. Now, before we do, I want to very quickly brush us up on the background information we all need to know, we all need to be aware of with regards to rational and non-rational numbers. Now, real numbers can be grouped into two. Remember, we have rational numbers and irrational numbers, which are otherwise referred to as non-rational numbers. So irrational numbers are otherwise referred to as non-rational numbers. Now, first thing first, let's quickly go over the basic definitions of rational and non-rational numbers. Now, of course, we did say that rational numbers are numbers that are whole numbers or numbers which can be written as a fraction. So any number whatsoever that you can write as a fraction, okay? Remember where you have your numerator, the dividing line, and the denominator. Any number whatsoever that you can write as a fraction, then that number is a rational number. And of course, you know the fraction can either be a proper fraction where the numerator is less than the denominator, or an improper fraction, which is otherwise referred to as a vulgar fraction, in which case the numerator is bigger than the denominator. So as long as you can write the number as a fraction, where clearly you have the numerator, the dividing line, and the denominator, then that number is a rational number. Now, of course, whole numbers too are otherwise fractions with a denominator of 1, but we don't normally put the denominator there, unless of course you're carrying out calculations involving fractions. Alright, so whole numbers too are pretty much fractions with a denominator of 1. Alright, so also moving a step further, all decimals which recur, or in other words, all decimals which repeat or terminate, can be written as fractions. And I've got examples here. Examples of rational numbers: 16. 16 is a whole number, which is the same as 16 over 1. Okay? 16 over 1. And then half, it's a rational number. 3.56, that is a terminating decimal. If it's a terminating decimal, it's also a whole number, because we can actually write that as a fraction. Okay? And then we also have minus 8. Minus 8 is exactly the same as minus 8 over 1. And then 1.3333, that is recurring. And if it's recurring, you can actually convert that to a fraction. And of course, minus 2 over 4. So all these are examples of rational numbers. Now, with regards to irrational numbers, or if you prefer, non-rational numbers, what are they? These are the numbers which cannot be written as a fraction. So numbers that cannot be written as a fraction, they come under the category of irrational numbers, or if you prefer, non-rational numbers. And any non-recurring or non-terminating decimal is said to be irrational. And here are examples. You've got your pi, the Euler number, which is denoted by the letter E. A third. What do we mean by a third? A third is when you have square roots or cube roots of non-perfect squares or non-perfect cubes. For example, root 5. Root 5 is an irrational number because it will give you strings of decimals that will not repeat or even terminate. And also the cube root of 7. So when you have the square root or the cube root of non-perfect squares, remember perfect squares are numbers whose square root will also give you whole numbers. For example, the square root of 4 is 2, which makes 4 a perfect square. The square root of 9 is 3, which makes 9 a perfect square. So those are perfect squares. But where you have the square root of the cube root of non-perfect squares or non-perfect cubes, then those are irrational numbers. Okay? Right. Now, let's move to the very first question. So if you check from the document I've attached with this lesson, there's question 1. For those of you who cannot see this question very carefully, you've been asked which of these are rational numbers. So look at all the numbers given from A all the way to L. Which of these are rational numbers? I want you to have a look and then pause the video for a while and then, give yourself a go. Try and identify all the numbers there that are rational. Okay? You can pause the video and once you're done for like a few minutes, you can then go over, continue the video, and then we continue, and you can also see whether you're right or not. Okay? Now, as a hint, 9 of these numbers are actually rational numbers. So which of the 9 are rational? Can you spot them? Can you identify them? Well, I'm going to show you now. For those of you who cannot pinpoint or pick out all the rational numbers, here are they. So A is rational, 30, which is the same as 30 over 1. It's rational. It can be expressed as a fraction where clearly you can see the numerator and denominator with the dividing line in the middle. Also 1.3, because 1.3 is the same as 30 over 10. Numerator, denominator, dividing line makes it rational. Okay? And then of course 3 over 5. So also is 16. The square root of 16 is 4, which also makes square root of 16 a rational number. So you've got 5 there. On this side, let's identify the 4 rational numbers. You've got 1.6. Yes, because 1.6 is the same as 16 over 10. Just like 1.3. So that makes it rational. You've also got 20 over 7. 0.7 is also rational. And last but by no means the least, 0.7 with a dot. Now remember, 0.7 with a dot is the same as 0.77777 and so on. To save you the hassle of having to keep repeating or keep writing 7, that's why you've got the 7 with the dot above it. So you put the dot above the digit that repeats, or if you like, the digit that recurs. Alright, so those are the 9 rational numbers from that list. I hope you all can see them very clearly. I hope you got them all right. If you didn't, just take note of the corrections. Let's move on to question number 2. Question number 2, reads, which of the following numbers are non-rational? Aha, non-rational now, if you like, irrational numbers. So which of these are irrational? Very quickly, let's identify them. Now I'm going to give you a hint. Again, you can pause the video and then give yourself that little challenge. Test yourself and see if you can correctly identify the irrational numbers from the list. Okay, now you have only 4, just 4 of them. Alright, so let's see if you can identify the 4 correctly. Well, here are the 4 irrational numbers from the list. The square root of 13 is non-rational because 13 is not a perfect square. So if you try to find the square root, it will give you an irrational number. Next up, the square root of 2.5 is also irrational because this is going to be the square root of 25 over 10. The square root of 25 over the square root of 10. Well, you have 5 over the square root of 10. 10 is not a perfect square. 10 is not a perfect square. So that is why the square root of 2.5 is not rational. Moving on quickly, and then pi, of course. Pi is a very good example of an irrational number. Pi and the Euler number E. Okay? And last but not least, the square root of 9 over 5. The square root of 9 over 5 is also the same as the square root of 9 over the square root of 5. And the square root of 9 is 3, but 5 is not a perfect square. 5 is not a perfect square. And so, because of that with 5, that makes the whole of that expression irrational. Alright? So those are the 4, 1, 2, 3, 4. Those are the 4 irrational numbers from the list. The others, the remaining, are rational numbers, and you can actually check. Moving on to question number 3 and 4. In question number 3, you've been asked, write 0.4 with a dot as a rational number. Remember, like I told you, whenever you have a decimal, be it a termination decimal or a recurring decimal, as it is in this case here, it's recurring, and the digit that recurs or the digit that repeats has got a dot above it. So this is a recurring decimal, and then want to write that as a rational number, meaning as a fraction where clearly you can identify the numerator, the denominator, and your dividing line. Okay, and the same goes for question number 4, where this time you have 2.4 dot. You want to write that recurring decimal as a rational number as well, meaning converting it to a fraction. So let's see, for those of you who have forgotten, we've done this in the past in class, but if you've forgotten, we'll quickly go over, just try and refresh your memory. Okay, so you have 0.4 with a dot. Remember, if it's recurring, for every digit that recurs, you divide by, can you recollect? Yes, 9, thank you. So you have 0.4 with a dot is the same as 4 over 9. And that's it. So 0.4 with a dot is 4 over 9. And that makes it a rational number, where clearly you can identify the numerator, the denominator, and the dividing line. Okay? So far so good. Let's move on to the next question quickly. Question number 4. You've been asked to write this time 2.4 dot as a rational number. Okay? Again, you've got 2.4 and then the dot is on 4, meaning the 4 repeats. So you have just one digit which repeats. And so if you are to write that down as a fraction, you take the number to the left of the decimal point, and then the one on the right, the bit that repeats, you divide by 9. Just like we did here. Alright, so you've got 2, 4 over 9. Now this is a mixed number. Now mixed number 2 is pretty much the same as a rational number, as a fraction, but then you convert that mixed number into an improper fraction, or if you like, into a vulgar fraction. Now 2, 4 over 9 as a mixed number, a proper fraction, as a beg your pardon, I should say, a mixed number to an improper fraction is what? You take the 9 to multiply by 2, and then you add the 4. 2 times 9 is 18, plus 4 gives you 22. So this mixed number as an improper fraction is 22 over 9. Yeah, thank you, 22 over 9. So there you go. And because you have, or you can clearly identify the numerator, the denominator and dividing line, that makes it a rational number. But I just want you to see how we handle the decimals, especially where you have a 0 to the left of the decimal point and where you have a number to the left of the decimal point. Okay? You follow exactly the same process. Alright? Moving on to question number 5. You've been asked to write 3.85 and you've got dots above 8 and 5. You've been asked to write that recurring decimal as a rational number. Again, we follow the same steps. Remember, there are the 2 dots. The number to the left of the decimal point, you bring that down, okay? And then for every digit that repeats, you have a 9 underneath. So the 2 digits repeating, 85 divided by 99. So there you go. That's a mixed number, which you now have to convert to an improper fraction. So 385 over 89 as an improper fraction, 99 times 3 plus 85. When you do that, you will get 382 over 99. And because clearly you can see you have a numerator, a denominator, and a dividing line. That makes it a rational number. So far, so good. And then question number 6. A student writes, all recurring decimals are rational. Do you think she's correct? Give reasons for your answer. Well, if you observe the previous examples we've been doing, they're actually recurring decimals, and we've been able to show that they are indeed rational numbers. Okay? So, yes, the student is correct. All recurring decimals are rational. But then you have to give reasons. What are the reasons? Now, all recurring decimals are rational because they can be expressed as a ratio of 2 integers. When you have a ratio of 2 integers, that is the same as what? Writing them as fractions. Exactly. Writing them out as fractions. So in other words, all recurring decimals can be expressed as a fraction, either proper fraction or improper, or like vulgar fraction. Or, I want to add to mixed number. Mixed number. Okay? Right, so there you go. All recurring decimals are rational because they can be written as a fraction where clearly you can identify the numerator and the denominator. It doesn't matter if it's a proper fraction or an improper fraction or even a mixed number, because of course, the mixed number can be converted to an improper fraction. Alright, so far so good. I hope we've been able to answer some of your questions for those of you who are having issues understanding how to convert from decimal, if it's a recurring decimal, to fraction. I hope by now you have a good idea of how to go about doing that. Alright, let's move on to the next question. Aha! Question number 7 now. Question number 7 reads, find the digit, or I should say, the first digit of the square root of, in A, 5.3. So you have to find the square root of 5.3 and then write down only the first digit. And then for B, the square root of 53, write down only the first digit. Remember the steps we follow? Well, if you don't, I will quickly go over to remind you. Alright, now A, you've got 5.3. Now 5.3, to find the square root of 5.3, we know 5.3 is not a perfect square. But think of a perfect square, which is before 5.3, and perfect square after 5.3. Now the perfect square before 5.3 is 4. So the square root of 5.3 will be between the square root of 4 and the square root of, what do you think is the perfect square after 5.3? After 4, the next perfect square is what? Can you guess? Yes, 9 exactly. So the square root of 5.3 would be between the square root of 4 and the square root of 9. Now we know the square root of 4 is, yeah, that's right, 2. And the square root of 9 is, yeah, thank you, 3. So the square root of 5.3 will be between 2 and 3. But remember, the question asks for only the first digit. So which do you reckon is the first digit? It's 2, exactly, and you're done. That's it. Let's go to the next one. This time you're going 53. You want to find the square root of 53, and you're asked to write down the first digit. To find the first digit. So again, 53. The square root of 53 will be between what perfect square and what perfect square? The square root of 53 will be between 49 and 64. Exactly. The square root of 49 is 7, and the square root of 64 is 8. So the square root of 53 is between 7 and 8. Therefore, the first digit of the square root of 53 will be, you guess, 7. Exactly. It will be 7. So there you go, that's the first digit. So the square root of 53 will be 7 point something. The square root of 5.3 will be 2 point something, alright? I hope you got that. Let's move on very quickly, because remember, like I said, if time permits, I want us to go over the last 3 questions from trigonometry, the topic we covered last week, and the questions I gave you as homework, because some of you want me to go over, alright? So let's quickly go over this so I can have time to go over the questions. I think there were 3 questions, questions 8, 9 and 10, exactly 3 questions, alright? So let's quickly move on and finish this. We have just 2 more questions to go. Question 8, you will ask to use the method of example 2 in the student book to find the value of root 5 to correct 2 significant figures. Now, I'm not particularly interested in a particular method here. I'm preparing you for the exam, so I'm giving you methods that will help you and save you time. And you can still get your answer right in good time. It saves you time and you end up getting the answer correct. Now, I'm going to ask to find the square root of 5 correct to 2 significant figures. The square root of 5 will be between what and what? Clearly between 4 and the square root of 5 will be between the square root of 4 and the square root of 9. So you have the square root of 4, which is 2, and the square root of 9, which is 3. Okay, now halfway between 2 and 3 will be what? 2.5, right in the middle, exactly. So you have 2.5. But then, okay, now let me just remove that for a moment. 2.5. 2.5 squared is 6.25, which is way too high, higher than 5. So we'll have to go to your left, okay, because the square of, the square of 2.5 squared is bigger. It's 6.5, 6.25 rather, is bigger than 5. So we have to go to your left. Now between 2 and 2.5 is what? 2.25. But then 2.25 squared is 5.062, which is slightly bigger. So you're gonna have to go again to your left. You keep going down. So from 2.25 go to 2.24, exactly. 2.24. Now 2.24 is 5.0176, which is still bigger, all right? But don't worry, because you're gonna have to get the answer correct to 2 decimal places. If you keep going down, 2.24, 2.223, it means this will be rounded down. Okay? And to 2 decimal places, to 2 significant figures. 1 significant figure, 2 significant figures. So that, of course, when we're going down, meaning it's really not important. So to 2 significant figures, the square root of 5 will be, can you guess? 2.2. Exactly. 2.2. Alright, next up, the last question now. Following the same steps, let's see if you can find the square root of 53 correct to 1 decimal place now, to 1 decimal place. So we're going to stop where we have 2 decimal places and then round. Either we round up or we round down. Okay? So, there we go. The square root of 53 will be between the square root of 49 and the square root of 64. And the square root of 49 is 7. The square root of 64 is 8. between 7 and 8, halfway between 7 and 8 is 7.5, right? So you have 7.5. Now, 7.5 squared is 56.25, which is way too hard. Way too hard. So we'll go down to the left. Between 7 and 7.5 will be 7.25. That's right, so 7.25. There you go. 7.25. But 7.25 squared is 52.5626, which is a bit less than that. So rather than going down, we'll be going up. So because we're going up, this will now be increasing. 7.25. Look at 7.26 next. Let's see what 7.26 will give us. 7.26 gives 52.7076, which is still close, but not quite. So it means this will keep rising. 7.27 and so on. But don't worry. To one decimal place, so this is where you stop in. But because this keeps going up, we will round up. And when you round up, you add 1 to that. Meaning to to one decimal place, which is pretty much the same as two significant figures here, but let's just stick with what the question says. To one decimal place, that's going to be 7 points. Can you guess? 7.3. That's right. 7.3. Correct to one decimal place. And that's your answer, okay? So that puts to rest any issues or any problems you may have with rational and non-rational numbers and the questions that follow. These are the typical questions you're likely to get on this topic. Alright, so having said that, let us try and go over the corrections to the ones we did last week, the questions I gave you last week. Okay, so from the last class, the trigonometry questions I gave as homework, questions 8, 9, and 10. Some of you were asking me questions, or some of you are telling me you don't understand how to go over the questions. Do not worry, I will explain in detail. For those of you who have done it, you might want to check if your answers are the same as mine. All right. So let's see the questions again. Questions 8. There's question 8. We're starting with question 8. You've been asked to make a suitable construction line, then calculate the length of PQ in figure 15.36. Now that's figure 15.36, which is built like a trapezium. But you've been asked to find the length of PQ. Look at PQ. PQ is all the way there, from P on the left all the way to Q on the right. You want to find that length. How do you go about doing that? Well, again, you may have to put a line there, and that broken line just helps you as a guide, and why you'll see shortly. Because when you put that line, you can then clearly see that you've got your right angle triangle there, which isn't important just yet. We'll get to that in a moment. But look, you can see clearly you've got 7 meters from S to R, meaning if you put a dividing line there, from P to that line will also be what? Can you guess? Yes, it will also be 7 meters. Alright? But we still need to find the length from that line to Q. Because remember the question says, find the length of PQ. So we'll have to find the whole length. And for us to find the whole length, you need to find x. And once you know what x is, you add it to the 7. And that gives you the whole length. So the problem now is, how do we find x? Well, it's not much of a problem, is it? Because now you have your right angle triangle. And from the right angle triangle, what do? You identify the sides correctly, the hypotenuse side, the opposite, the adjacent, and from that on, you decide on which of the trig ratios you use, either sine, cosine, or tangent. Alright? So let's go, shall we? So we are identifying the sides now. Using the right angle triangle, you've got to your right here. The side directly opposite the right angle, that is your what? Yes, the hypotenuse. Alright, and then the given angle, the side opposite is your opposite side, and the third side, your adjacent. Alright, but you don't need that side. We don't have any information there, and we don't need it. The side we're looking for the x, and that's your adjacent, and the side we're given is the hypotenuse. So let's get rid of that side and the arrows. Now when you do that, you can see clearly we have the sides A and H. Right, so you have A and H, A and H. Remember what trig ratio do you use? A and H are car. Yeah, that's right, so you use cosine. And so the cosine of the given angle, the cosine of 40 degrees will be equal to A, which is the adjacent, and that is the side we're looking for, your x, divided by the hypotenuse, 8. And from there, you know what we do? We cross multiply exactly. And then when you cross multiply, your x will now be equal to 8 times the cosine of 40 degrees. And from the fourth figure table, the cosine of 40 degrees is what? If you check, and make sure you're looking in the right table. Don't look in the table of sine, don't look in the table of tan, look in the table of cosine. And when you do, you realize that the cosine of 40 degrees is 0.7660. And then you multiply that by 8, and when you do that, you should get 6.1284. But your answer correct to 2 decimal places, you stop in there, 8 is greater than 5, so you round up. So when you round up, you add 1 to that. And so you have 6.13 meters. And that is the value of x. But remember, we're not done yet. Don't stop there. The question says find the length of PQ. P goes all the way from there to your left to that point, to your right. So now that we have x, what do you reckon with the length of PQ? You add the 2 lengths. This, the 7 meters, and the x. And that gives you the length of PQ. Yeah, and that's what you do. Therefore, the length of PQ will be the 7 meters plus your x. Remember, your x is now 6.13 meters. And you've got 13.13 meters. And that's your answer. Now, for those of you who did it and you got it right, well done. And for those of you who didn't quite know, or you're not sure how to go about it, I'm sure now you know. Alright? So, 2 more questions to go very quickly. Question number 9. Someone really told me or sent me a mail saying, she, or I should say he, didn't quite understand how to solve this. It's not hard. You just meant to think a little bit. You know, think a little bit. So let's see. You have figure 15.37. It's a side view of a table supported by legs inclined at theta. Look at the theta there. To the horizontal, as you can clearly see. Now, if the table is 76 centimeters high and each leg, there's a leg, is 80 centimeters long. You have to calculate the value of theta. So we're looking for the angle this time. Looking for the angle. So how do you go about doing that? Now, of course, I've put a broken line there, and clearly, if you observe, the length of that broken line is the same as the height of the table, and that's 76 centimeters. But then again, you can see clearly we have a right angle triangle there, which can clearly be identified by that little box, the right angle. So given the right angle, let's see if we can find theta. Yes, we can. But remember, you identify the sides correctly. Identify the sides correctly. The side directly opposite the right angle is your hypotenuse. Yes, that's your H. The side opposite the given angle is your, as normal, opposite. Okay, so give me O and H, O and H, O and H. What trig ratio do you use? O and H. Oh, so, exactly. So S, which is for sine. So the sine of the theta, which is the angle we're looking for, will be opposite. Opposite is the 76 centimeters divided by the hypotenuse. The hypotenuse is 80 centimeters. Now, of course, the sines, the units will cancel. And you have 76 over 80. Now 76 over 80 as a fraction in its simplest form is what? So you have sine theta with 19 over 20. And 19 over 20 as a decimal is 0.9500. Now, to find theta, what do? Theta will now be the inverse sine of 0.9500. So from the table of sine, try and look for where you have 0.9550. If you find it, you realize that that value corresponds to angle 71.8 degrees, okay? Therefore, the value of that theta is 71.8 degrees, okay? if you did that and you got it right, well done. And for those of you who struggled, well, at least you can see that it's not really as hard as it looks. Some questions, you know, when you read them, you tend to be put off, but don't let any question put you off. Give yourself a little push, give yourself a little challenge, and realize that it's not as hard as it looks. That's the way it goes. That's how you get better with maths. Alright, so moving on to the very last question now, which most of you really struggle with. And again, it's not hard. Let's see. Let's go to the questions together. Question 10 now, you have an isosceles triangle, has sides of length 10 centimeters, 12 centimeters, and 10 centimeters. So two sides are equal, and that's why it's called an isosceles triangle. An isosceles triangle is a triangle where two sides are equal. Okay, so the two sides are equal are 10 centimeters long each. Now, A, you will have to use Pythagoras rule. For those of you who have forgotten Pythagoras, by now, I mean, you should have gone back to revise. Use Pythagoras theorem or Pythagoras rule to calculate the height of the triangle, and then for B part, use trigonometry, that is SOHCAHTOA, to calculate the angles of the triangle. So quickly, let's go over, shall we? So there's your isosceles triangle, 10 centimeters, 12 centimeters, and 10 centimeters. Okay, and we have that dividing line, the broken line in the middle. Okay, and that broken line is the height, which we've denoted by the letter X in this case. Okay, so using Pythagoras, remember Pythagoras says that the hypotenuse, the square of the hypotenuse, is always equal to the sum of the square of the two other sides. So you have to identify the hypotenuse first, and the hypotenuse is always equal to the side that is exactly opposite the right angle, which in this case is your 10. So the hypotenuse square, and then that line divides the base of the isosceles triangle into two equal parts. There's going to be 6 centimeters there and 6 centimeters there as well, because when you add the two together, you get 12, which is the length of the base of the isosceles triangle. Alright, so taking this right angle triangle, you have that the hypotenuse squared is the sum of the square of the two other sides, which you have clearly denoted there, and I've color-coded to show the different parts. Now you have 10 squared, which is 100, is equal to x squared plus 36. Okay? Now making x squared the subject, you have 100 minus 36 is equal to x squared. Now we subtract 36 from 100, get 64. If 64 is equal to x squared, therefore x is equal to what? The square root of 64 exactly. And 64 is a perfect square, so the square root is 8. That's right. So the height of the triangle, that is the value of x, is 8 centimeters exactly. Alright? Now, very quickly, let's look at the B part of the question. The B part reads, use trigonometry to calculate the angle of the triangle. Again, very quickly, you have that. So we're looking for the angles inside the triangle. The base are equal, and I've used p to denote that. Then very quickly, well, you realize that is a trig ratio we're going to use. So theta, cos theta is 6 over 10. Now making theta the subject, we'll have theta, the cos inverse. And from your table of cosine, when we form the table, that gives you 53.13 degrees. That's for this angle, which is the same as that angle. When you add the two together and you subtract from 180, you get the third angle. Alright? So this times 2 gives you that. When you add the two together, you get that. And so the third angle will be when you subtract this from 180 degrees. So the three angles inside the isosceles triangle are as follows. You have 53.13 degrees, again, that's for this, and for that, and then the third angle is 73.74 degrees, alright? And so that's it, and I'm sure now you clearly know what to do. Alright, so let's stop there for now. Thanks so much for your time. I'll see you again. Stay safe. Bye.